speaker to have Professor Alberto Marino from University of Oklahoma. Alberto also actually is the interim director of the Center for Quantum Research and Technology at OU, and with whom actually Purdue, as well as our friends at IU and of them, we have been discussing many interesting collaborations. Alberto is experimental quantum optician, okay, and particularly he does very interesting work applying quantum optics to quantum information science and quantum sensing, quantum metrology, which is the topic of the seminar today. Before Oklahoma, he did a postdoc at East PQI, and even before that, he got his PhD from Rochester East Optics. So we're very happy to give, I believe, our last PQC seminar online this semester, and look forward to discussions and more collaborations opportunities to coming out of these interesting discussions. Go ahead, Alberto. Thank you.
So thank you for the introduction, Yang, and it's great to be visiting if it's virtual. Was actually there back in 2016.
Yeah.
It would be nice to be back in person, but well, given the circumstances, this is better than nothing. So just to check, everyone can see the slides?
Yes.
Yes.
It's
yes. So as Yang mentioned, I mean, we've been discussing quite a bit recently on possible collaborations, and I hope that this talk can help to get some of those collaborations moving forward. So I hope that there's questions, please feel free to interrupt, and hopefully this will lead to interesting discussions. So what I want to do today is tell you a bit about the work that we have been doing in my group on quantum enhanced sensing with light. As Yang mentioned, we're a group doing experimental quantum optics. So we're approaching all of this from the quantum optics perspective, in the sense of what can we do with quantum states of light? How can we take advantage of them? And in particular, how can we use them to enhance sensing applications? So this work has been funded in part by the Keck Foundation and the National Science Foundation. And it's part of, we recently started our Center for Quantum Research and Technology, and this is part of that center here at the University of Oklahoma. So probably needs no introduction with its audience, but as you all know, there's now a very significant push to do or to use the quantum resources in a way that is not possible with classical systems in order to enable what's now known as quantum technologies. And of course, this is not a new thing. I mean, people in AMO have been doing quantum science for a very long time to try to enhance measurements. And a particular case, the atomic clock, which are the most precise devices that people have built ever. The interesting thing now is that these devices are being taken from the lab, where you have optical tables and a lot of equipment needed to really integrated systems. So you can actually now buy an atomic clock that is a chip scale clock, and it's not as precise as the ones in the lab, but it's better than what was there before, and it's taking advantage of the work that came out of research in the labs. Another example of technology that has moved from the lab to actual products has to do with quantum communication, where you can now find companies that sell devices to do quantum key distribution over short fiber networks. And moving forward, what I think will be the most significant impact of quantum technologies, at least in the short term, has to do with quantum enhanced sensing, that is the ability to use quantum resources to enhance sensing applications. And again, there's been a lot of work in this area. Back in 2003, the group of Claude Favre and Hans Backhourt showed that it's able to use quantum properties of light to better estimate the pointing stability of a laser beam of light. And they actually coined this as a quantum laser pointer back then. But it's the idea that you can do better with quantum resources. There's been work on using atomic systems as antennas, such that you can actually enhance the sensitivity in measuring electric fields. And as you probably all know, LIGO is now an example of quantum enhanced sensing, where routinely now they use a squeeze light, quantum light, in order to enhance the sensitivity of these interferometers for gravitational wave detection. So again, this might be a bit introductory for this audience, but I just want to get everyone on the same page. When we are thinking about doing a detection, what we do is we do a series of measurements to estimate a given parameter. So we can think of a measurement problem as an estimation parameter problem. And if you just do an error propagation equation, you find that the relationship between the uncertainty in estimating a parameter P, what you want to measure, depends on two things. The denominator is a property of the detector or the system that you're using. This is pretty much how much what you're measuring changes when the quantity of interest changes. And more importantly, at least from our perspective, what we're doing is a numerator, which has to do with the measurement uncertainty. And this numerator is limited by quantum mechanics. In light, it's limited by the shot noise limit. And it turns out that quantum mechanically, we can actually get quantum states of light that have reduced noise, and I'll get to more details of what that means, in one of the properties of the light, and that allows us to do better than we can do with classical systems. So it's this idea that using quantum states of light, we can actually enhance the sensitivity of devices. So this is kind of the really big idea in which some of our research is based. So due to the applicability of light in a lot of sensing scheme and that it can interact with a lot of systems, there's been a lot of schemes that have been proposed and a lot of proof of principles experiments that have been implemented to show how light can be used to enhance systems beyond the classical limit. And these are just a few examples. The list is long, and this is not meant to be comprehensive in terms of lists or references. But for example, as I just mentioned, LIGO is now routinely using quantum states of light to enhance the sensitivity of gravitational wave detection. There's been experiments that show that by using light that has reduced noise properties in the polarization, you can actually enhance Faraday rotation measurements for things like enhanced magnetic field sensing, characterization of materials, displacement measurements like the ones I kind of briefly mentioned before, but you can use this to measure the displacement, let's say, of an AFM microscope, things like that, where anything that has a displacement that needs to be performed to do a measurement, you can actually enhance that. And there's been recent experiments, well, not so recent now, but in terms of getting biological measurements below what you can do with the standard quantum limit or with classical light. So if you want to get a bit more information, I recommend that you look at this review paper that we wrote recently. It has a bit more references and applications of quantum states of light. But for our work in particular, the question that we were asking, is it possible to interface quantum states of light with real-life devices? So there's all these applications that have come up. I mean, I would say LIGO is a real-life device, of course, and there's things coming out of it. But if we want to really get quantum resource of this quantum enhanced sensing to a broad applicability, we need to start interfacing with devices that are regularly used for applications for everyday use. So our approach back then, we started this project about 5 years ago, actually, was to interface with plasmonic sensors, plasmonic structures. And the reason for that is that plasmonic sensors are widely used already in chemical and biological sensing. They can be probed with light. And more importantly, they have been shown to operate at the classical limit given by the shot noise limit. So this last part is really important. If you have a system and you cannot operate at that limit anymore, or you cannot reach that limit, then using quantum light will not really lead to any enhancement at all. Okay, so if you think of any quantum sensing approach, at least in terms of optical-based sensors, what you have is something like this, where you're going to have a source that generates your quantum states of light. And here, this doesn't have to be optical photons. They can be in any place in the spectrum of the electromagnetic field. Then you have your sensor that you're interfacing with. In our case, these are the plasmonic structures, as I'll mention. And then you have some type of measurement to characterize or measure the property that you're trying to detect. So I will start my talk by giving an overview of the beams that we generate, the entangled beams, some of their properties, and also how we can characterize them in terms of some entanglement measurements. I will then describe how we interface the quantum systems, the quantum light, with these plasmonic structures or sensors. And once we have all that, I will start to show some of the results that we were able to get in terms of quantum enhanced sensing. I will describe some of the fundamental limits of these approaches. And then at the end, if there's time, I will briefly touch on some new work that we're doing to extend these approaches to parallel sensing, where you can sense multiple things at the same time beyond the classical limit. So let me start with the source. So again, this might be a bit basic, but so we're all on the same page. We are working with what we call continuous variables. And what we mean by these are variables of the electromagnetic field that have a continuous range of values. And if you look at an electromagnetic field, you can write it as an in-phase and out-of-phase component. And these two operators are what we call the quadratures of the field. And these are what we routinely measure in our experiments. They're called the amplitude and the phase, even though they're not strictly speaking amplitude and phase of the field. Think of it as a phasor in phase space. So these two variables do not commute, which means that they have an uncertainty principle. And this is actually what leads to the state of light having noise. And this is consistent with this shot noise or the minimum noise that we see in line. Turns out that coherent states, which are the quantum representation of classical states, are able to minimize this uncertainty, and they have the same noise in both the quadratures. And this is what is known as a shot noise limit. And this will serve as a measure of whether something's quantum or not. So being able to beat this limit will tell us that something is quantum. So again, I mentioned that you can think of this amplitude and phase in terms of a phasor diagram. So you can think in terms of phase space, where you have one axis representing the amplitude, the other axis representing the phase. And if you look at the distribution of the electromagnetic field, you have that the distance from the origin to the center of the circle gives us the amplitude here. The angle here gives us the phase. But what we're really interested in here is this little fuzzball that we have here, which corresponds to the noise. This tells us what the noise in the system is. So if we look at the projection in one axis, we get the noise in the amplitude. If we look at the projection in the other one, we get the noise in the phase. And for a coherent state, this is a nice little circle, and this is the minimum uncertainty. And one of the nice things about using these properties of light is that we can directly characterize their noise properties through noise measurements. So what we do in the lab almost every day is measure the noise properties of light. So we're just measuring noise and trying to get information out of those noise measurements. Okay, so how do we generate anything that is different than these coherent states? So it turns out that we can use nonlinear processes to modify the statistics of the light. And there is this process that does what's called squeezing that depends quadratically on the creation and destruction operators of the field. So it means that it either absorbs or emits two photons into the field simultaneously. And what this operation does is that it takes an initial coherent state that is a circle, and it actually squeezes or pushes in one direction. So you get reduced noise in one direction at the expense of added noise in the other. We still have to satisfy the uncertainty principle, so we cannot be below the shot noise in every single direction. So what we get from something like this, if you look at this picture, is that in one direction, the one here at 45, for example, you get a reduction in the noise. However, in the other one, you get excess noise. And if you take the product of these two, you still have to satisfy the uncertainty principle. So this is what we mean that we're able to beat the shot noise limit. We're able to beat it in only one particular direction, or let's say variable, not in every single direction. So this becomes important when we want to make a measurement that only depends on that quadrature and not more than one quadrature. So it turns out that
is the largest S possible?
So people have been able to get up to 15 dBs of squeezing, which corresponds to an S approaching a value of 2. So if you think about what that means, that means that you have only a few % of the noise left. So 10 dBs corresponds to only having 10% of the shot noise left. And every 3 dBs, of course, you go down by a factor of 2. So the record right now is actually done by a group in Germany, Schnabel's group, which is working on interfacing with gravitational waves. So they're really pushing the envelope there on going down that far. So something, I'm probably getting a bit ahead of myself, but something that's important is that these states are really fragile to losses. So at some point, you are dominated by the losses you have either in the optics to get from one point to the other, the detection system. So you have to work on all of them, not just the source.
So in practice, experimentally, you always saturate the uncertainty in practice?
In practice, it's almost never.
That's it. And how far is from the saturation?
It depends a lot on the losses as well. So the problem is anytime you have let's assume that you had a perfect squeeze state in the sense that you have a minimum uncertainty. As soon as you have losses, it becomes a mixed state, and that adds noise to the system. So for any real application, you are always going to have some losses, and that's going to make it asymmetric in the sense that it's not going to be minimum uncertainty. People have come close, but not at the maximum levels of squeezing.
I see.
The more squeezing you have, the more sensitive you are to losses. So it's kind of a double-edged sword having more squeezing. So it's good for applications, but you are more sensitive to everything, which also for some applications that's actually good. And for some it's a problem. So one of the things, how big that S is depends on the amount of that nonlinearity in the system. So you really want to get strong nonlinearities in your system in order to get large levels of squeezing. So just as an illustration of what this means is if we had this minimum axis aligned with the x-axis, what we call the amplitude of the field, what we have is the following. So if you can think of a coherent state, what gives the shot noise limit as being composed of photons that are randomly distributed in time. So this gives us Poissonian statistics in the arrival of photons or the detection that we have here. And that is what gives rise to this shot noise. This is what gives rise to this classical limit. And when we have an amplitude squeeze state, what that means is that we have better ordering in time in the distribution of photons. So this allows us to have less noise in the amplitude of the field, for example. So it turns out that there's different types of squeeze states. And another one, which is the one that we actually use in my lab, is what is called a two-mode squeeze state. They're also known as twin beams. And what happens here, if you remember, I mentioned that to get squeezing, you need to generate two photons into the fields. Those two photons do not need to be generated into the same field. Sorry. So what could happen is that we generate two photons, one into what we call the probe, and a second one into what we call the conjugate. You can look at the literature, and in parametric down conversion or the single photon limits, they call this Sigland and Leitler, but they're the same thing. So what happens is that at some point you generate a pair, some later time you generate another pair, and so on. So you generate a stream of pairs of photons. If you were to look at a single state by itself, you would actually find that it's quite noisy, actually noisier than a coherent state. The important thing here is that if you look at what you measure with the other field, due to the fact that every time you have a photon here, you have a photon here, the fluctuations are perfectly, in the ideal case, correlated, such that if you look at the difference in the signal, you actually are able to cancel the noise, even this randomness in the arrival of photons, and go below the shot noise. And that's what gives you reduced noise properties. So what we have in these twin beams is a relative ordering between the arrival of photons in one beam and the other. So there's always some ordering that comes in terms of these squeeze states. So this emission of photons in pairs is what gives us amplitude correlations between the fields. And if you look at a phase space diagram where you look at the amplitude of the probe and the amplitude of the conjugate, what you find is that you get an ellipse as well that has reduced noise properties along the amplitude difference. That is, you have correlations in the amplitudes of the fields. The process, of course, also needs to conserve energy, and this will lead to phase anticorrelations in the field. So you will get, if you look at the phase quadratures of the probe and the conjugate, you're going to get something at minus 45 degrees, which means that you will get reduced noise properties along the plus 45 or the phase sum of the fields. And as I will show a bit later, being able to measure both of these joint quadratures is enough to tell us properties about the system, in particular that they have entanglement between these variables of these two fields.
So Alberto, one question. I mean,
sure.
What decides the distance between the probe and the conjugate? How is that you manipulate that experimentally?
What do you mean by the distance?
Okay, I mean, you have two detectors. There are two beams, right? You're saying it's a twin beam.
Yes.
So my picture is that these are two beams that are separated in space, right?
Yes.
So what defines that distance?
Well, I mean, if coming out of the source, it has to do with the phase matching conditions that determines what is the most efficient direction in which the beams are emitted, and that has to do with conservation of momentum, and I'll get to that in a bit. Afterwards, it doesn't matter. You can propagate them as far as you want. The main thing is that there's only a correlation time between them. So you have to detect them within that correlation time if you want to see some of this interference. But these beams you can send in different directions if you want.
No, the direction, yes, but I'm saying the distance between the two. What defines the separation between the two?
I mean, that physical separation is whatever you want. You can move this with your optics as you propagate through the experiment. As I mentioned, the more important thing has to do with when they're emitted at the source. And that has to do with, as I'll explain a bit, with conservation of momentum in the four-way mixing process, or the process that you use to generate them.
So when they are generated, you can think of them as going.
Right, when they're generated, they're going in two separate directions. So you can actually, say that again?
You can think of the origin from one point, but going with an angle between these two rays.
Yes. So inside the source, they are generated at the same location. That's right. But they can be generated depending on the process, either collinear or in different directions. But they are generated going in different directions. But inside the process, they are generated at the same spatial location. I'm not sure if that answered your question or not.
I mean, I want to know, okay, because I am coming from the side of neutrons. So that's, in neutrons, we do something similar. It's not with pairs, but we have control of the distance, okay, between the separation between the two beams. And we do that with magnetic fields in a particular instrument. So my question here is, do you have the ability to control the distance between these two beams in the pairs?
Yeah, there are two, think of them as two independent laser beams. I mean, they're not independent because they're entangled, but think of them as two probably separate laser beams. So you can do whatever you want with them like a laser beam. So you can move them around with lenses, mirrors, whatever.
Yeah, but I mean, I'm not saying to move these here or here.
No, you can separate it. They're physically separated to start with. So you can actually control them independently.
And doesn't matter what is the smallest distance and what is the largest distance you can?
No.
No, I'm saying, what is the smallest? The smallest could be as small as you want, or the large as large as you want, or what?
You can combine them as you want. I mean, for example, if they have polarization, so you can combine them, for example, with a polarizing beam splitter. There's also nonlinear processes where these beams are collinear. They can have different polarizations, but they're still collinear, so you can distinguish them through polarization, but they're collinear. So there's no minimum or maximum distance.
I see. It's interesting. I would like to learn better how is that you generate that, because this beam could be used. Okay, yeah. If that's the case, they could be used for scattering purposes to get, additional correlation functions.
I think there's definitely been work, people looking at scattering with these types of beam. And I know you've worked on some of the theory of this, so it would be interesting to discuss further.
Right, because I think that could be something interesting. So that's the reason why I'm asking you.
Okay, yeah.
How much you can manipulate these things, etc.
Yeah, no, you can manipulate the distance completely. It's, just like two beams of light, you can pretty much combine them and separate them as long as there's something to distinguish them.
That's pretty interesting.
Okay, so the next question is how can we generate these beams, right? At least in the optical domain, we need a nonlinear process that can generate two pairs of photons simultaneously. So one of the most commonly used one is based on parametric down conversion, where what happens is that you absorb a photon at one frequency, and then to come down, you emit a pair of photons with reduced frequency such that you come down to the same energy level. The problem with this is typically implemented with crystals, nonlinear crystals. The nonlinearities are weak. So in order to get large levels of squeezing, what people do is that they put them inside a cavity, enhance the interaction strength through the buildup of fields in the cavity. And this makes it possible for them to get large degrees of squeezing. Another possibility is to use four-wave mixing, which is based on a Chi-tree process. The idea is similar, but instead of absorbing a single photon, you absorb 2 photons and then emit 2 photons. And these are the type of experiments we do in my lab, and I'll go a bit more into details of how we implement them. And the main idea in all of this is that we're always generating pairs of photons together, and this is what leads to the quantum correlations. So it is actually with a parametric down conversion with these OPOs configurations, with this type of system, a bit more robust than these cavities, with kind of semi-monolithic designs, that people have been able to reach those 15 dBs of squeezing in the generation of squeeze light. Okay, so let me now jump directly to what we do in my lab to generate these beams. We use an atomic system in our experiments, and the reason for this is that it gives us a large nonlinearity when we're close to resonance. And what we do is that we combine a strong pump beam with a weak probe beam, and as a result of the four-way mixing process that we have in the cell, we amplify the probe and we generate a new field, the conjugate. If you look at the energy level diagrams, a bit different than the one that I showed before, but the idea is the same. We absorb a pump photon, emit a probe, absorb a pump, emit a conjugate. So we are absorbing 2 pump photons, and then in this process, emitting a probe and a conjugate photon at the same time. So if I were to look at this system, and I were to look at the spectrum that I would get if I were to scan the frequency of the probe, it would look like this, where these 2 dips are just the absorption of going from one of the ground states to the excited state, the other ground state to the excited state. But the important thing here are these 2 peaks, which corresponds to the gain of the process. And this is where we get the four-wave mixing going. So this frequency would correspond to what we're calling the probe here. This frequency would correspond to what we're calling the conjugate here. And then what we do in order to characterize the quantum properties is that we measure the intensity of the probe, intensity of the conjugate, and then look at the noise in the difference signal. And this allows us to characterize this kind of intensity or amplitude difference noise that I was describing before. So with our system, when we do these types of measurements, this is what we get. We have the shot noise limit, which we obtain by just using 2 coherent state, in a sense, laser fields that are well balanced, so we can cancel classical noise. And it gives a measure of the shot noise level. We typically always normalize everything to the shot noise level. And once we do the experiments with the twin beams, the probe and the conjugate, we get a curve like this. And what we can see in our experiments, at least in this case, we were able to get 9 dBs of squeezing. And this corresponds to having only 13% of the standard of the shot noise limit. So if you were to look at the phase space diagram that I kind of showed before, the ellipse would look like this, which is highly, highly correlated in terms of the amplitudes of the field. And I want to point out that this is actually measured level of squeezing. So if you take into account detection efficiency and everything else, the source actually generating quite a bit more squeezing than what we're able to measure. And another thing that's important, at least in our experiments, not for every application is this useful, but one of the properties of using atomic systems is that the bandwidth of the generated photons is narrow, 15 to 20 megahertz, mainly determined by the strength of the pump and other parameters. And this allows efficient interaction with atomic systems. And this is not going to be the focus of the talk today, but we also have efforts in moving in this direction to interface quantum states of light with atomic systems.
What sets this very small frequency scale, like 0.05 megahertz, where this changes rapidly?
Okay, here there's several things. Here, there are a lot of it. This depends on the parameters. So it depends on the susceptibility, the nonlinear susceptibility of the medium. And a lot of it has to do with you have to be in Raman resonance between the pump and the probe in order for this to be efficient. So this gives us the line width. So typically the line width is limited by that, and that's what gives the 15 or so megahertz line width. But a lot of these details on how fast this grows depends on the detunings that we use, depends on the angles. So it all has to do with the susceptibility, and we can control that to some degree by changing the parameters of the source. There's another interesting thing that happens, and that's if there's a delay between the time you measure one photon and the other, you get some oscillations in the spectrum, and that's just the fact that the power spectrum is the Fourier transform of the correlation function. So if you have a delay in the correlation function, that's just oscillations in the power spectrum. And some of that also leads to this maybe going up a bit farther. But a lot of it has to do with the properties of the system, and we can control it to some degree, but it's not independent of the level of squeezing. So typically what we do is we optimize for squeezing more than bandwidth in our experiments.
And all your light beams are around 790?
795, right? So we are at the D1 line, which is 795. The frequency separation between the probe and the conjugate is twice the hyperfine splitting. So these two are about 6 gigahertz away. And we typically detune the probe about a gigahertz away from resonance, although we have some results where we're able to tune this to resonance with reduced noise properties. But we operate close to resonance, maybe not that close for cold atoms, which is, again, one of the things we're working on. But we're close to resonance, and they're all really close in frequency. So this has advantages and disadvantages. The advantages are that if we want to interface with, let's say, other rubidium atoms, we can interface both fields. The disadvantages is that they're so close in frequency that it's really hard to separate, let's say, any scattered photons from the pump, to separate them from the probe and the conjugate. So there are things that become easier, things that become harder as a result of this. Okay, so this is just one of the properties. We have these reduced noise properties, but another property of these states is that they have entanglement. And again, this is just the typical entangled system where you have spin up and spin down. If you were to measure the property of one of the systems, you know the properties of the other. So this is what we have for a discrete system. If we now go to the continuous variables that we have in the experiment, the summation over states is transformed to an integral. And what determines the properties is this function f. And in this case, we have what we call continuous variable entanglement. If we cannot factorize this function into a product of a function that depends on one system and a function that depends on the other. So if we're not able to do this, then we cannot factorize this wave function into a product of two wave functions, one for each state. So what we need to do is that we need to look at collective variables, that is variables of the two systems that we're considering. And given the correlations that we have in the system, it makes sense to look at the amplitude difference and the phase sum. And we define these joint quadratures this way such that the shot noise limit is still normalized to 1. So this 1 is still our shot noise limit. And it turns out in these papers down here, they showed that by looking at these joint quadratures, you can get an inseparability criterion such that if you have reduced noise in the amplitude difference and the phase sum, and you add them up and that's below 2, that's enough to tell you that you have continuous variable entanglement. Given that each of these variables or joint noise properties is equal to 1 for a coherent state, if you get squeezing in both of them simultaneously, you know right away that you have entanglement between the quadratures of the system. In order to measure this type of variables, we need to do something more complicated than intensity measurements. We do homodyne detection. I won't go into a lot of detail explaining it, but what we do is that we combine a local oscillator with the beams that we want to measure. And by changing the relative phase between the local oscillator and the beam that we want to measure, we can measure either the amplitude or the phase quadrature, such that if we were to have two measurements, one for the probe and one for the conjugate, and we scan them together, we can measure the amplitude quadrature in one, the amplitude quadrature in the other, and then look at the difference signal. We can measure the phase quadrature and phase quadrature, look at the sum, and then see what happens. So as we scan the phase of the local oscillator, we get signals like this, where you go above the noise, below the noise. So typically, the way that you can think of this is that we're doing a tomographic measurement of that ellipse. So at some point, you're looking at the minimum noise and the maximum noise. So the main points here to focus on are the lower ones, which in one case for the sum gives you the phase sum, the noise in the phase sum, and the minimum here gives you the noise in the amplitude difference. And what we can see for this case, we have still 4 dBs of squeezing left in both of these joint quadratures, which means that we have entanglement between the systems. So the next thing, and this is kind of what I was getting at with the direction of emission, the process also has to conserve momentum. So given that we start and end in the same energy level in the process, the photons that are involved in the process need to conserve momentum by themselves. So what this means is that if we take two pump photons that are going in one direction, if the conjugate is going in one direction, sorry, if the probe is going in one direction, the conjugate has to be emitted in the other direction to conserve momentum. And this is what's called phase matching, and this leads to anticorrelations between the emission direction of the probe and the conjugate. So we need this phase matching for efficient four-way mixing, but it turns out that it's not an on and off thing. There's a range of angles in which you can get phase matching. So for example, if we were to work here, we have a minimum angle between the pump and the probe. If we were to operate here, we have a maximum angle. So we have this range of angles between the probe and the pump over which the process can happen. And the nice thing about the system that we have is that due to the large nonlinearity that we have, we don't need to have a cavity around the system. And this means that the system can support a lot of spatial modes. So what this means is that if we put a mask in at the entrance of one of the beams, and it has a pattern, let's say, in this case was at number 200, as you can see here, what happens is that the process by itself is going to generate the conjugate that has the same pattern as what we put in the probe. And it's rotated by 180 degrees to satisfy the phase matching condition. So this by itself doesn't give us any quantum properties. These are just classical intensity measurements. But you can perform the type of measurements that we did before and show that more complicated patterns, like our logo, and here this was supposed to be a smiling cat, but it didn't turn out that friendly. And it's mainly limited by the resolution of the system, but you're able to show that we have entanglement with these complicated spatial patterns. And something I want to point out briefly, because I think I'm running a bit behind, is that some of the properties of these entangled beams is that in addition to having entanglement over the whole system, we're going to have that small subregions are independently entangled with the corresponding region in the other beam. So we can think of this as pixels in an image, such that this pixel is only entangled with this pixel is only entangled with this pixel. And this will play a role in what I will show at the end in how we can actually implement the parallel sensing configuration. Okay, so now let me move to the next portion of the talk. I don't know if there's any questions at this point.
Well, I mean,
the property of entanglement between the two and the squeezing, these properties go together, or these are two separate aspects?
They go together. I mean, if you have, typically when we measure the intensity and measure the intensity squeezing, that gives us a measure of the squeezing or the noise properties of the amplitude difference quadratures. So the squeezing measurement gives me only half of the measurements that I need to say that I'm entangled.
But once you generate these pair two-mode squeeze light, they are automatically entangled. That's the way you describe it, right?
Well, in theory, yes. In practice, not always. For example, people doing parametric down conversions and OPOs, they had a really hard time. They were able to get really large levels of intensity difference squeezing for a long time, except that they had problems with getting the phase sum to be squeezed. That is, they were able to show half of it, but not the full entanglement criteria, because their system, the fact that they have a cavity that was coupling phase noise into their system and made it such that they didn't have entanglement. In our system, we have a symmetry between the two quadratures. There's nothing to break that symmetry. So in general, if we have squeezing, it's almost guaranteed that we'll have entanglement, but of course we need to check that always to make sure that that's the case.
So I have a related question that, I'm not understanding exactly that kind of criterion. Okay, smaller than 2. I mean, the sum of the square is smaller than 2.
Yeah.
So what I don't understand is, suppose that I start changing the intensity. Suppose I can change the intensity. There will be a moment that even though I can, still have these two variables, x minus y plus, there will be a moment that the system should behave classically in some way. So do you see that? I mean, do you see that if you increase intensity in some way, you have a transition from something that is smaller than 2 to something that is not smaller than 2. So you lose entanglement, because otherwise, you know, what I don't see is that this entanglement should disappear at the classical level. Okay.
Well,
and what is the trick?
Well, the first thing to point out here, these are correlations between the noise, right? The fluctuations in the fields, not the mean values.
Yes.
So I think there's a misconception in the sense that if you go to the bright limit, and that's where we operate, we don't lose the entanglement. The fluctuations are still correlated. We're always generating photons in pairs, no matter. So let me back up a bit. Let's see.
I'm not questioning that part. What I'm asking is, why is this entanglement? That is the question. So entanglement, it's a quantum property, okay?
Yes.
And what I'm saying is, if you continue increasing the intensity, there should be a transition at a certain point. You're telling me you are looking at the noise. I understand, but how do you understand that? How do you understand that you go to the classical limit in intensity and still you have an entanglement that you see through the noise? Because
this, the main thing is these ellipses, right? So what does it mean to have more intensity? The only thing that will do in this phase space is to take this ellipse and push it somewhere else. If I change the intensity, I'm not changing the ellipse. I'm not changing the distribution of these noise properties. I'm just moving this ellipse around. So in principle, I could displace this ellipse anywhere in phase space, which means I could have whatever intensity I want, but those fluctuations, that noise is still going to be correlated and entangled.
I mean, it's interesting. I mean, I need to think, but it's interesting, you know.
No, I know. I mean, I think a lot of these things come more from thinking of things in terms of photons and what the photons are doing, as opposed to the quadratures. And for these measurements, the intensity itself, the mean values, do not play any role. I could either be what we call vacuum squeeze states, in which the mean value is 0, or I could displace them. So think of it this way. If I were to generate these beams of light with the vacuum that is with a mean value of 0 like this, and then I perform a displacement operation, I'm still not losing the quantum property. The correlations are still there. You of course need to make the right measurements to get access to those entangled properties. We need to make noise property measurements. If we were to count photons and do coincidence measurements, for example, it will be impossible to see these things because you will have a lot of background or noise, let's say, from the displacement event. But if we are to measure the quadratures of the field, then we can have access to those correlations. And we don't care about the mean value or the displacement.
It's interesting, again, I insist, because you see, there is here a philosophical issue about the transition from classical to quantum, because in some variables, I mean, by increasing the intensity, you are going to the classical limit, but you're telling me that if you look at the noise, you still see the quantum correlations.
Yes.
And
Gerardo, maybe we can have the extend discussion a little bit, and yeah.
Okay, yeah, let's keep going. Okay, so as I mentioned, the experiments that we're doing have to do with enhanced sensing. And in our case, we were looking at the interface with plasmonic structures. And the first thing that we had to check is whether these plasmonic structures actually preserve the quantum properties of the light. If they didn't, then there wouldn't be any point of really trying these experiments. So the first thing that we did, and I'll just talk about these experiments briefly, but if you want more information, you can look at this paper. We generated these entangled beams of light with the four-way mixing process, had the probe and the conjugate, sent both of those to two separate plasmonic structures, and then did homodyne detection to characterize the entanglement properties. And one of the things about this is that in these structures, there's going to be transmission of light. So effectively, what we're going to have is a transfer of photons to plasmons in these structures back to photons. And just to talk a bit about the plasmonic structures that we used, we had an array of holes. And if we zoom in, we see that those were triangular holes of about 200 nanometers in scale with a 400 nanometer pitch. We used triangular holes mainly because our collaborators at Oak Ridge, who we were working on in that project, had been fabricating these structures, and they were resonant at our wavelength. And a few things that happened, and I'm sure you all know, is that when you have light incident on these type of structures, you can get extraordinary optical transmission, which means that a significant portion of the light that is incident is transmitted to the structure, even though through diffraction theory, you wouldn't see that much light going through. And for this wavelength and this structure, we actually get localized surface plasmons for this system. And the other thing that we get from having an array of holes is that we get a resonance in the spectrum. And for our particular structures that we were using, we're able to get in the order of 50, 65% transmission to the structures. And this is kind of what that measurements and some of the simulations look like. So we did the experiments. One of the nice things about localized surface plasmons is that they can support a lot of K vectors or incident angles. And what we did just to illustrate this point is that we took our four-way mixing process, generated these images that are entangled with each other, and then looked at what happens after going to the structures. So what we found is that the spatial configuration or spatial information in the beams is not significantly changed by the plasmonic structures, and this was expected due to this fact over here. However, this is still nothing quantum. We're just looking at the intensity profiles. And what we do then to look at the quantum properties is that we perform the type of measurements that I explained before in terms of homodyne detection and look at those joint quadratures. Without the plasmonic structures, we start with about 3 dB of squeezing in both joint quadratures. Once we put in the plasmonic structure, the squeezing is reduced to about 1 dB, but we still have entanglement between the system. So the main thing that we get here is that this reduction in squeezing is consistent with the loss that is introduced by the plasmonic structure, but more importantly, that we're able to preserve the quantum properties of the light. And this was, again, the first step to be able to use this configuration to do enhanced sensing. So let me quickly move to what is the main topic of the talk, and that's with the quantum enhanced sensing and how we can use these systems. And just to kind of, again, get everyone on the same page, we're using these plasmonic structures as sensor, and they operate based on 2 principles, this extraordinary optical transmission, which allows us to probe the system with light. And the second one is that we have this resonance as a function of frequency when we interface with these structures. So assume that we have this resonance profile in terms of transmission. If we were to probe the system with a single frequency, a laser beam, we will get a given transmission. When the substance of interest is next to the plasmonic structure and changes the local index of refraction, what we get is a resonance shift, which then corresponds to a change in transmission. And by changing this change in transmission, we can then estimate the resonance shift and estimate the change in index or the presence of something next to the sensor. So what is the minimum resolvable change that we can get with such a system? Can be given again by this equation with just error propagation. So there's a couple of things here that matter. The first one has to do with the properties of the sensor or the slope. The second one has to do with the properties of the light. So what limits what is the minimum resolvable change in index that we can have? So as I was saying, when we get a shift of resonance, we get a change in transmission. So the limitation is going to be how well can I distinguish these 2 levels of intensity when I perform my measurement. So there's 2 ways to enhance the measurement, that is for a given change in index, a given change in resonance. I can distinguish these 2 levels. One, if they're farther apart, and that has to do with increasing the slope of the system, that will make a bigger change. The second one has to do with reducing the noise. So if I have smaller noise in the measurement of each beam, I can measure 2 transmissions that are closer, which means that I can measure smaller changes in the index of refraction. So this points to 2 mechanisms. One is reduced noise in the electromagnetic field by using quantum properties, which is what we're using in our experiment. And the other one is by designing better systems that have increased slope. And this, of course, is not quantum, but it's another way to enhance the sensitivity. So what is the level of enhancement that we expect? If we were to look at just the ratio of the sensitivity with classical resources to the sensitivity with quantum resources, what we can show is that this is directly proportional to the level of squeezing. So it depends on the square root of S, because when we talk about squeezing, we talk about variances. Here we're talking about the standard deviation, which actually gives us how sensitive the system is. So if we were to look at these quantities and just do some simple calculation, we find that the enhancement factor for 10 dB of squeezing, which is more or less what we can achieve in our experiments, we should get an enhancement factor of 3 if we had perfect transmission. But as you can see here, one of the disadvantages is that the enhancement goes down as the transmission is decreased. And this has to do with losing the quantum properties. This also points to some of the advantages of these states, and that's that no matter how much loss you have, you're always going to get an enhancement. This is not the case for every quantum state. So in a sense, quiz states are robust against imperfections in this regard, but you do pay this penalty that you lose enhancement as you reduce the transmission. Okay, so in terms of our experiments, what we do is that we take our four-way mixing process and generate probe and conjugate beams. We take the probe beam and send it through the plasmonic structures. And what we do after that is that we detect it. We then take the conjugate, which serves as a reference, goes to a different detection. We then do measurements and characterize the system. And just briefly, we actually, in order to really control the experiment and the index of refraction, we put the plasmonic sensor in a controlled environment in a sealed chamber where we have a buzzer that drives pressure waves inside the chamber, which allows us to control the index of refraction in a controlled way. And we can actually calibrate this, and this allows us to make measurements of the system. So as you can see here, this is kind of actually what illustrates the type of enhancement that we can get. We drive the ultrasonic buzzer as its resonance frequency just to get a good signal. And we can compare the configuration that we have here with classical systems by just replacing these entangled beams with classical coherent states of the same intensity. And what we get in that case, if we drive the system hard enough and we consider with coherent states, we get a given modulation, we get a peak here that is a measure of the change in the index of refraction. If we repeat these measurements with the twin beams, we get a reduction in noise. So we get an enhancement in the signal to noise ratio of the signal. And this pretty much illustrates the type of enhancement that we get for this type of systems. And for this case, we start with 9 dBs of squeezing, but due to the losses, we were left with only about 4 dBs of squeezing at the measurement itself. So what happens then is that if you reduce the modulation of the index of refraction, at some point you won't be able to resolve it with classical coherent states. But if you probe the system with the twin beams or the quantum correlated beams, you actually have still a good signal to noise ratio. So you're still able to measure these smaller changes in the index of refraction. So what we did in the experiments is that we performed the measurements at that resonance frequency at that peak, and then scanned the modulation, as a function of time. And what we find is shown here, where we look at the modulation signal as we reduce the voltage that we're applying to the buzzer, which is proportional to the change in index. And as that modulation is decreased, what we see is that we come down in signal as expected, and at some point we reach the noise given by the shot noise limit. So at this point, we cannot distinguish the signal from the noise anymore. And that is what limits the resolution of the system. If we were to perform the same measurements with twin beams, we can see that we can actually go farther below we reach the noise level given by the twin beams. So it's this change in where the signal meets the noise that leads to an enhancement in the sensitivity. And in order to get some measurements out of this, what we do is that we take the signals, calculate signal to noise ratio, and then look at the signal, get a mean value of the signal, and then calculate what is the 99% confidence level with which we can distinguish our signal from the noise. And this gives us the sensitivity of the signal. In this case, this corresponds to changes in the index of refraction of 8 in 10 to the 9. If we repeat these measurements with the entangled twin beams, we get a noise reduction or a sensitivity that goes from 8.6 to 5.5. And this corresponds to an enhancement factor of 1.6, which is consistent with the 4 dBs of squeezing that we measured. If we were to take the bandwidth into account for these measurements, we get a sensitivity of 5.5 times 10 to the minus 10 refractive index unit per root hertz. So the question now is whether we're comparing with the optimal classical measurement that we do. So we were actually measuring with, let's say, the equivalent classical system. As I mentioned, what we did was to take, instead of the twin beams, we take classical beams of the same intensities, And that's what corresponded to our coherent state measurements. But it turns out that if we consider the photons that are probing the sensor as the resources to perform this measurement, we can actually do better if we use a single coherent state as opposed to the configuration that we use. In practice, this is hard because every laser, every beam has some technical noise. So we can actually perform measurements to estimate or cancel that technical noise, and then from there estimate what we would get in terms of a single coherent state. And that is given by this dashed line here. The main point to illustrate here, even if we take the optimal classical configuration, we're still doing better by using the quantum resources than the optimal classical configuration. So we're able to beat the optimal classical configuration with this system. The question we can ask them is, can we do better? Is it possible to do anything different than what we're doing to better take advantage of the quantum resources? So in order to answer this question, we need to look at theoretical limits that are given by the Kramer-Rao bound for a given system. And what we have here is that this bound tells us that the minimum uncertainty in the estimation of a parameter is greater than or equal to the inverse of the Fisher information. And this Fisher information gives a metric of how well we can distinguish probability densities in terms of measurements or states. And there's two types that you'll see typically in the literature. One is what's called the classical Fisher information. And this is distinguishability of the measurements. That is, given a distribution of measurements, how well can we distinguish these measurements given that the parameter in the system changed? Now, by using tools from quantum mechanics, what people have been able to do is to optimize over all possible measurements that can be performed. And this makes this bound independent of the measurement strategy. So what you're doing here in a sense is you're finding how much you can distinguish the properties of the system, that is the state of your system at this point, how much that state changes given a change in the parameter you're estimating. And the nice thing about this quantum Fisher information is that if you're able to saturate that bound, you know that you're doing the best measurement that you can do to take advantage of your state and system in terms of using quantum resources. So we performed some theoretical calculations, and what we showed is that for a coherent state, you get something like this, where here we're plotting the uncertainty in the transmission through an optical element multiplied by the number of photons that are used to probe the system. You get a linear behavior as you would expect. This is how the shot noise scales with losses, so this is no surprise. What we found is that the Fock state gives you the ultimate limit. That is, this is the best quantum state that you could ever use. And this is actually not a new result. Other people have shown this. But what's more interesting for us is that if we use the quantum system that we have in our lab, you get something like this. You get a significant enhancement for those transmissions. And as you increase the level of squeezing, you approach farther and farther this ultimate limit. So as I said, 15 dB is about the most that people have been able to do. That's approaching the ultimate limit in sensitivity. And the advantage of this is that you can generate these states, the twin beams, with a lot more photons than you can Fock states. So this overall can enhance the absolute sensitivity of measurements. And the other thing that we found is that our detection scheme saturates the bound. So that means in terms of detection schemes, we cannot really do any better than what we're doing already. So let me ask you, John, because we're already almost at 10 o'clock. At what time should I wrap up right now, or should I just keep going, or?
Maybe if you can wrap up in 3-ish minutes.
Okay, so let me just talk about the next slide, and then I'll wrap up after that. So it turns out that what we're doing is just measuring transmission, but anytime you have a resonance, and this is applicable for any resonant sensor, not just plasmonic sensors, you're going to have a corresponding phase change. So in terms of measuring transmission, you can also make measurements or do an estimation through phase estimation. And there's advantages and disadvantages to this. Transmission-based measurements, one of the problems, given that it depends on the slope that we have, you cannot operate at the peak transmission. You always have to operate a bit of the peak transmission. And this is a problem for quantum states because you're going to have some loss associated with that reduction in transmission because of this. The advantages of the phase-based estimation is that you can operate at the maximum transmission, and that's also where you have the maximum slope for the phase. The disadvantage is that you have more complicated measurements that you have to perform in order to get access to this information. But anyway, just to make the long story short, what we found is that for simple or most common line shapes like Laurentian and Gaussian, the phase-based estimation always performs better than the transmission-based one. So in principle, we should be able to, instead of estimating transmission, estimate the phase and take better advantage of quantum resources in order to do this. So with that, let me just skip over this last part. And I just want to acknowledge the people that were involved in the group. This is more or less a 4-year-old picture of the group. But the main people that work on the experiments that I showed here, the postdoc Asha Kumar, who's now back in India as a faculty, Javad Dorwan, who's a grad student who's almost graduating, and Tim Woodward, who has done a lot of the theory calculations and things having to do with the quantum kernel bound. There was a former student in the group, and also collaborators at Oak Ridge. So with that, I would like to conclude. The main general points I want to make is that quantum states of light can enable quantum sensing configurations that can go well beyond the classical limit. It's always important to study these fundamental limits to see if we can do better and how we can better take advantage of quantum resources. And finally, even though I didn't get a chance to present this, it is possible to take advantage of both the spatial and temporal properties of these systems when we're doing quantum enhanced sensing. And this can lead to imaging applications, and there's actually a whole subfield that is called quantum imaging that studies the use of the spatial properties of light for imaging applications. So if you want to get a bit more information on some of the work I presented, these are some useful references. So with that, I would like to thank you all for your attention.
Thank you very much, Alberto. Great. So sorry we squeezed your talk a little bit, but
no, it's fine. It's exciting to hear these discussions. I think that's the purpose of this talk, to get these discussions going.
Exactly. We want to have some conjugate between your talk and the interesting discussion. Okay. I hope. Or maybe I can ask you this question. Sure, so I guess one, at least a very interesting result you showed is you're doing these measurement of the change of index refraction of gas, right?
Yes.
That's in that chamber. And your technique, this quantum sensing, improved the detection resolution of that delta M by about factor 2.
That's, yeah, we were close. I mean, 1.6, yes, but we were, yeah.
Right, yeah, on that order. This is compared at comparable intensity, because you're comparing to a situation where you would just be using a single probe light, right? A standard, that would be your comparison, right?
Right. So
is that at comparable intensity of the light, and yeah, also does this measurement delta N sensitivity depends on the intensity of light used?
So okay, so yes, these are all compared with the same intensities of light. So what we're saying here is that what we're treating as our resources is how much light we put into the sensor, the plasmonic structure. At the end of the day, that's going to be any limitation that you have with these systems. So let me just back up a second. I think one of the questions that we typically have to answer and address, which is a really significant question, is that how can we really do better than classical systems? In a classical system, if I increase the intensity when I'm probing something, if I increase the intensity, I can increase the sensitivity. The sensitivity goes as the inverse of the intensity or square root, depending on whether you look at variance or standard deviation. So just by increasing the intensity, I can increase my sensitivity. So we always have to be aware of that. And a lot of the experiments we do are just showing with comparable systems. So we need to look at applications where we are really at that fundamental limit in which we cannot increase the intensity anymore. That's what happened, for example, in LIGO, that they cannot really increase the intensity inside their interferometer because of technical issues, heating, and everything else in their system. So what they can do in that case to go farther is to use quantum states of light. I'm sorry, my computer kind of blinked for a second. So what you can do there is that you need to find these limits. So this is why we're considering this as the resources, because at the end of the day, this is what's going to limit what we can do. These are comparable measurements for these particular experiments. I I just glossed over it, but we're using 60 microwatts of power probing the sensor. We can increase this power further in our experiments. We're limited mainly by the photodiodes that we use to measure the properties of the light, not the actual sensors or the source. But we compare everything with respect to these 60 microwatts when we're doing these types of measurements. This single beam equivalent, which would be the optimal classical system, would correspond to having 60 microwatts hitting that plasmonic structure. Did that answer your question, John?
Yes, it's to some, yes, thank you.
So let me ask you the following question. I mean, two correlated questions. So when you are comparing the best classical strategy with the twin beams, you said, well, of course, I mean, there are ways of, just putting just one coherent beam there, and we can do better. However, we do better with the twin beams. Fine. Now, two questions. First, the obvious question is, can you get more than twin beams? I mean, can you get, like 4, 8, whatever, okay, beams of the things that if you can entangle all of them, clearly you are also going to increase sensitivity, okay? That is the obvious way of doing metrology, quantum metrology. So that's one question. And the second question, which is related, is in your experiment, doing the best classical strategy, if instead of using coherent, you were using two beams which are not entangled, but they are squeezed. They are not entangled. So suppose I could produce experimentally two beams which are unentangled, but they are squeezed instead of coherent.
Yes.
What is the difference?
Let me start with the first one. In principle, yes, you can generate beams more than two entangled beams by doing not four-way mixing, but I mean, the simplest thing, for example, using different sources and then mixing the beams optically, and that can lead to multi-partite entanglement, or you can do different processes. The one thing that I want to comment there is that having more entangled beams is not always better. It depends how you use your resources. If you were to just let me say, if you were to just do what you have here, where you get one of the beams that's entangled through here, and then let's say this would be 7, 8, however many other beams you have, that would not be better because you're not using the quantum resources to probe the system. And that comes to your second point. If I were to have,
but what if you use 4 and 4?
If you use 4 and 4, it would be exactly the same as you have here.
There is no difference. I mean, theoretically, there is a difference.
Well, it is a difference if you probe with every system, right? If I have a distributed sensing and I have measurements with if every single beam has information about the system, yes, I agree with you. You would do better. But if you think about what you have here, only one beam out of the two has information about the system, not both.
Mm-hmm.
So you do not get that extra square root of n, where n is the number of entangled beams enhancement, because you're not probing with all the systems, with all the beams.
Mm-hmm.
And that comes back to your second question. What would happen if I were to have two single squeeze beams? So one of the things that I want to point out before I answer that question is that in this experiment, we're not really taking advantage of entanglement. We're taking advantage of reduced noise properties.
Mm-hmm.
So there are experiments and other, let's say, approaches like quantum illumination and things like that that take advantage of entanglement as opposed to just reduced noise properties. In that sense, if I were to think of having two single squeeze beams, one here and one here, it turns out that the best thing you can do is not to even consider this squeeze beam, just consider one squeeze beam that is going through the sensor, and that would actually do better than the configuration that I have here.
I see.
The only problem with that is that it's really hard to get something that it doesn't have technical noise at low frequencies. So one of the advantages of doing things like this, where you have two beams of light, is that you can do differential measurements, and that allows you to cancel any classical technical noise. And that makes the system more robust. So there's advantage in one end, but you actually lose a bit in the quantum enhancement. So if I were to look, I don't have the figures here, but let me just come back here. If I were to look at, for example, this system where I have two mode squeeze states with 5.8 dBs of squeezing, and then a single mode squeezing where I'm only using that single mode to probe the system, the curve will be slightly lower than this one.
I see.
And again, the problem here is that we're not using both entangled beams to get information about the system.
I see.
Okay, let's see, any last questions? Okay, maybe one last thing I can ask you, maybe it would spirit a possible experiment. I mean, here you're putting, actually I realize there's two. First of all, you're putting this gas in this chamber where you have the plot structure. You
Yes.
can replace, you can also put some solid state material on top of your plasmonic structure. That's okay with your measurement, right? And you can sensitive to some maybe phase change in that material. This is one question. And second, if you can just clarify again the role of the plasma structure, because it seems this is optional. You can do all these measurements even just without the structure, just by having your probe beam through some medium, right?
Yes. So let me start with the second one, and then I'll come back to the first one. So yes, this is general. As I said at the beginning, we're approaching this from the quantum optics and quantum enhancement perspective. The plasmonic structure was just a way to say we can actually interface with structures or systems that are used in real life devices. Anything that shows a resonance, for example, will work exactly the same, whether it's an optical cavity. So anything that has a resonance will show the same behavior. We can replace the sensor with anything else and get similar things. Also, without a resonance, if you get changes in transmission, we can get the same thing. So yes, the plasmonic structures are not critical for these experiments. The first question you answer is yes, you can put a material. The main thing would be that it doesn't really kill the transmission of the light through the system. If you cannot get transmission, then, or reflection, I mean, you can also operate some of these in reflections. So the main thing is that you don't get a significant loss of light when you add the extra material to the plasmonic structures. But yes, you can operate, for example, if you have even a material that is not transparent at our wavelengths, you could build the structures on one side and then look at reflection instead of transmission.
Great. I'm sure we will follow up on some of these various very interesting possibilities that you described.
I think there's a lot of possibilities for collaboration.
Yes, let me ask you a technical question. Sure. I mean, when you were talking about phase estimation and transmission, so is that from the technical point of view, the equivalent thing as saying that you are doing amplitude amplification versus phase estimation? When you're saying transmission-based estimation, is that amplitude amplification? Is equivalent thing? I mean, I've never seen it this way. I mean, that's the reason why I'm asking.
What do you mean by amplitude?
Well, that you estimate the amplitude. You have amplitude and phase, essentially.
Oh, yeah, okay, yes.
So it's equivalent. So you are comparing amplitude amplification to phase estimation, and you are arguing that there are pluses and minuses in each.
Yes, but I think the main point I was trying to make here is that with it, you will get an interplay when you use quantum resources. I mean, the point here is anytime you have a resonance, you're going to have a corresponding phase shift, right? So when the light goes through this system, you can either estimate a change in transmission or estimate a change in phase on the light after it goes through the system. So you can use both of those approaches. And both of those will give you information about the change in index of refraction in this case. So the main point I was making here is that for typical line shape like Lorentzian and Gaussian, you're always going to do better with phase when you consider these fundamental limits in terms of the quantum current raw bound. It turns out that you have an interplay between transmission, because here you cannot operate at the peak. You're typically operating somewhere down here where you have an interplay between slope and transmission, and that gives you the best sensitivity. If you were to have something more like a square shape, let's say line shape, you can actually do better with transmission in some spaces or some parameters than phase. So it will depend at the end on the line shape, which one does better. But for the most typical line shapes, Lorentzian Gaussian, you will do better by doing phase-based estimation. That is, looking at the estimating what is the change in phase of the light after it goes through a system. It turns out that there's some recent work of this theory work that tells you that you can do even better if you're able to measure both transmissions and phase simultaneously. Unfortunately, that's not possible to do with quantum states. So.
No, I was asking you a technical question because, you know, there are different algorithms to do both. And I mean, I hear just to compare. I mean, I've heard what you say experimentally, okay? But I just wanted to know exactly what was the meaning of transmission.
Okay, sure.
Connection,
okay, yeah.
To put the dots.
Yeah.
Okay, thanks. I think it's very interesting.
Thank you.
Yes, thank you so much, Alberto. Generally, a lot of discussions.
Yeah, it's been...
And yeah, I'm sure we'll discuss more. And so this concludes the seminar. And this is actually the last seminar of the semester. Thank you, everybody, for attending. We'll resume the online. We'll still have to do the online mode again in the spring, but hopefully things will return to the real reality later by summer. But I will resume the seminar series hopefully in the mid-January when the new, late January when the new semester starts. So thank you, everybody. You can watch out the emails from David. And if people still have more questions, they can stay in the virtual room, like in the red side. But thank you, everybody. Thanks, Alberto.
Thank you.
Thank you very much.
Thanks.
See you. Have a nice day.
Yeah. Bye.
Bye.